Okay, so welcome back to the class. So now we are in chapter 4, which is the sequential circuit design. In the previous chapter, we have learned how to design one of the uh, digital circuit, which is the combinational circuit. So in digital circuit, we have two main type of circuit. The first one is combinational circuit, and the second one is sequential circuit. So the first one we have learned already how to design the uh, combinational circuit, and now we will learn another kind of digital circuit, which is the sequential circuit. So what is the difference between sequential and combinational circuit? So we need to go back to the definition of the combinational circuit. So for example, we have the circuit here in the box, combinational circuit. So if we have input A and B, and we have output F. So for the combinational circuit, whenever one of the input or both of the input change, whether change means that change the state. For example, if A, from logic high to logic low, or from logic low to logic high, that we call change. Change the state of the circuit. So whenever one of the input or both change, this will immediately affect F, and F immediately change the input. For example, if we have the an OR gate, right? If one of the input change, so we at the output immediately we have the output change the value. But for sequential circuit, the behavior of the circuit is a little bit different, where the output uh, the output of the circuit not only depend on the input, but also depend on the previous value of the output. All right. So for example, if the previous value of the output is 1 and the input change to, for example, AB, right? We have AB. So initially we have 0, 0, and also we have F. AB 0, 0. Here we have F, for example, equal to 0. And when we change to 0, 1, B change to 1. So F is depend not only on AB, but also depend on the previous F. Yeah. So if the previous F is 0, the output may be 1. But if the previous output F is 1, the output may be different, right? So that is the behavior of sequential circuit. So what we learn in this chapter is this. First is we look at the fundamental circuit of the sequential circuit, which is the latch and flip-flops, and also sorry, I need to change this also. Right, this is not chapter 3 anymore, but this is chapter 4, which is C sequential circuit design. Right. So in this chapter, we will learn the fundamental of the sequential circuit, which is the latch and flip-flops, and we will look at a more bigger circuit, which is the register, and the variation of register, which is the shift register, the counter, and also the memory circuit. And we will look at the application of the sequential circuit, which is what we call the FSM, or finite state machine, and also what we call the algorithmic state machine, or ASM chart. Yeah, this is actually the same thing, but the representation is a little bit different, right? We will see later. So this is the explanation of what is sequential circuit. So just like I said, the sequential circuit is the circuit in which the value of the output depend not only on the present value of the input, but also on the past behavior of the circuit. Yeah? So this is the sequential circuit. So the first sequential circuit that we want to look at is the what we call the latch. Yeah? So this is the basic or fundamental of the sequential circuit actually. So when we look at the latch, and this is the basic latch circuit, where we can see that the input to this gate is actually the feedback from the output of the circuit. All right. So this feedback will give you memory actually. It will define the behavior of the sequential circuit, where the input, the input here and the output here is also depend on the previous output value. So this is the what we call the SR latch, or set reset latch, and the circuit that we usually use is looks like this, and this is the characteristic of this SR latch. So you actually learned this already in digital electronic. So this is just a revision, where we can see that the behavior is like this: if S equal to 0 and R equal to 0, and the output is actually no change. If it is 0, means that if the previous value of the output is 0, then the output is no change. It will stay or remain 0. If the previous value is 1, it will remain 1. So no change. But if R equal to 1 and S equal to 0, QA will be 0 and QB will be equal to 1. And if S equal to 1, R equal to 0, QA equal to 1, QB equal to 0. And if both are 1, QA and QB are 0. Yeah. So this is the characteristic of the SR latch. And when we look at the timing diagram, yeah, the output, the relation between the input and the output. So here is how it is actually based on this characteristic. So for example, if R S equal to 0, yeah, initially at T1, and as R go down from 1 to 0, and here S is go up here and go down here. And let's look at the output QA, right? So the QA here is actually based on QB. This arrow shows that this one will affect this one first before go to QA. Because if we look at the circuit S here, if S change, it will change QB first before QA. All right, because QA will depend on QB. All right, see, QB will be the input of this gate, and you have QA. That is why you have the arrow like this. When this change, it will change QB first before it change the the QA. Yeah? It actually has a very small delay before this one. So if we look carefully in the simulation, in the timing simulation, what we see in is not like this. Yeah, it is actually looks like this: QA, QB. So if we have QB is from 1 to 0, right? So if we have the grid, QA will go to 1 a moment after QB go down, right? So we have a small delay here, all right? And this is illustrated by this arrow. Okay, so S will affect QB first before affect the QA. Right, that is mean by this arrow. And this is the characteristic of the SR latch based on this characteristic table or truth table. And we go to another latch circuit, which is gated SR latch. Yeah, this one we have clock, right? And this is the basic SR latch, and we have clock signal here. And if we have clock, the characteristic will be like this. If the clock is 0 or not active in this case, so the Q, the output is no change. Yeah? And it is not depend on an S and R anymore. It will always no change. Yeah? So S and R is now don't care if clock equal to 0. But if clock is active, now SR will give the output. It is based on the previous one as well. So when 0 0 we have no change. If 0 1 we have 0. This is Q, this Q, yeah, QA, right? If set equal to 1, so we have 1. If 1 1 is don't care, right? And this is the graphical symbol of the SR latch, right? Now come to the next latch, which is a very important latch and very useful one, right? In digital design, in digital circuit, right? Which is used very often in designing the digital system, the D latch, right? And this is gated D latch where we have the clock. So the behavior or the characteristic is like this. When clock is 0 or not active, we don't care about D. So D is either 0 or 1, but QT is don't change, remain the same, right? If clock not active, like this, see, if clock not active, if Q equal to 1, it will remain 1 until the clock is active again. Then it will go down to 0 based on this D, because when we look at this characteristic, if D equal to 0, yeah, when clock is active, when D equal to 0, Q also equal to 0. When D equal to 1, Q also equal to 1, right? So here also the same. See, when clock is not active, this part, we will see that the output here will remain the same. If it is 0 here, it will be 0 until we have the clock active here, and it will go to 1, follow the D here, right? So that is the behavior of the D latch. And now come to the next one, which is the one that is actually used in designing the circuit. This is D-latch is not really used in the circuit, but it is a basic of the behavior of D flip-flops. So now we go to D flip-flops. So what is the difference between flip-flops and latch? The difference is that the latch, when we look at here, it is level sensitive. The output here is it is based on the clock, and it is level sensitive to the clock. For example, when clock active, all right, so D will always, or Q will always follow D. All right, so see here, when clock active, so we have this, right? But for flip-flops, it is age sensitive, means that it is only change the level, the output will change the level only at the clock edge, whether positive edge or negative edge, right? So this is the circuit of the D flip-flops, and this is a negative edge triggered, where we have two D latch connected like this, master, slave, and we have the clock like this, and we invert the clock for the slave, and we have the D flip-flop. Okay, so let's see how it works. So if we have the clock like this, and we have D here, D go to 1, and of course, because this is D latch, it will QM, the output of the master will go to 1 immediately, all right, because the clock is active. Go to 1 until here, go down, but the clock is not active, so QM will still remain 1 until the clock is active here, and because D is 0, it will go down to 0 until here the clock is active, go up. So this is the output of this master, which is the latch. And the output of the slave, where the input is the output from the master here, and the Q is the output of the slave latch, and this is Q. And again, the Q will active when this clock is active, or this clock is 0, because we have this clock is 0 because we have the inverter here, right? So basically it is active low. We look at the clock when it is low, so the input is QM. So here, because the clock is active for slave, the clock is active, so it will go up, because QM here is equal to 1, go up until here the clock is not active for slave. The clock is not active, and because the clock is not active, the previous output is 1, it will still remain 1 until here the clock is active for the slave. And if the clock is active, and because this is 0, it will go down to 0 and done. Go up again here. So when we look at this, look at D and look at this, we can see that here, if this is negative edge triggered, all right, so we will see that if positive, when D equal to 0 here, so nothing changed, yes, but here negative edge, all right, the negative edge of this clock, D equal to 1, so here we see Q go up to 1, here positive edge, no, because positive edge, so it will remain the same, 1, remain 1 until the next negative edge here, and because here D equal to 0, it will go to 0. Go here, this is no, look at the negative, because D equal to 1, it will go up. So we can see that by connecting the two latches like this, and we have this, we can create what we call the D flip-flops. All right, and this is exactly the behavior of the D flip-flop, and it is negative H triggered. All right, and it is a most useful circuit in designing a digital system. We will use these D flip-flops again and again and again later on. All right, but now how we want to create the storage element or latch in Verilog, right? So last time when we synthesize or do the coding for the uh, combinational circuit, yeah, when we code for combinational circuit, when we use if statement, all right, I said that you need to have the else statement, right? Because if in this case, if control equal to 1, A equal to B, but what if control equal to 0? You haven't, you not specify what if control equal to 0. The Verilog compiler will assume that A will remain A when control equal to 0, right? This is the same as we write the code like this. If we have if control equal to 1, A equal to B, right? But if we don't have the else statement, the Verilog compiler will assume that we have this. Means that if control equal to 1, yes, A is equal to B. But if control equal to 0, A will remain A. So this imply memory circuit. Okay. And this will give you a latch in Verilog. So it will give you this. Okay, you will have the circuit like this. And this is a D latch. So when control equal to 1 means that A will equal to B, and when control equal to 0, A remain A. So this is behavior of the D latch. Okay, so that is how we create the D latch in Verilog. Very easy actually. Yeah, if clock Q equal to D, same as this one, right? We have D input and we have clock input, and if clock active, the output Q is equal to D, and if clock is not active, the output Q will remain Q. And this is how we create the flip-flops, D flip-flops. So when we look here, the declaration part is the same, but the difference is that in flip-flops, to create a flip-flops, in the sensitivity list, in for the latch, we list all the input, right? B control, or in this case is D clock. But in or to create the flip-flops, we need to use this keyword, post H or neg H, negative H or positive H clock. All right, so this is the keyword. When you have this, the Verilog compiler will create the flip-flops for you. If you write like this, yeah, so no need to have if clock, yeah, just q equal to d, then you will have the flip-flops. So in this case, you will have positive h, which is the clock, and this is d, this is q, right? So you will have this when you write the code like this. Very easy, very straightforward. So to create the flip-flops in Verilog is easy. Now we will look at the how we use the assignment statement to create the sequential circuit. So before this, yeah, when we assign or use assignment statement, what is assignment? Assignment is this, the equal symbol. Remember when we write the code, we have A equal to A and B or C and D. So this is called assignment. Sorry, this. All right, when we write A equal to A and B or C and D, so this is called assignment. That's the equal symbol is the assignment. And before this, yeah, up until now, before chapter 4, the symbol of assignment is this, equal. All right. But in Verilog, we actually have two type of assignment. First, if we write like this, we call it blocking assignment. There is another type of assignment, we call it non-blocking assignment. And the symbol is this. This is not less than or equal, but this is equal also, but we call it non-blocking assignment. So what is the difference between the two? Now, to look at the difference, we need to consider or look at this example. For example, we want to create a cascaded flip-flop like this. The connection is like this. And we use this to define or to describe the flip-flops, these two flip-flops. Yeah, you use non-blocking assignment. And Q1 is equal to D, which is correct actually. And Q2 is equal to Q1. Or Q2 is Q1 is assigned to Q2. D is assigned to Q1. It should be correct, right? But by using blocking assignment, because the blocking assignment, the Verilog compiler will evaluate the statement and always block in order in which they are written. Means that the blocking assignment, when we have many statements in one always block like this, the Verilog compiler will evaluate this and this in order, and after evaluate all the statement, it will create the circuit. So this statement, the second statement, will depend on the second statement. So when we write something like this, the Verilog compiler will make us an assumption that, or conclusion that, because Q1 equal to Q1 equal to D, Q2 equal to D, therefore Q1, sorry, Q1, therefore Q2 should be equal to D, right? And the circuit will be something like this. You can get the circuit either this, D, Q2, not like this, or you may have something like this, yeah, D, Q1, D, Q1, and Q2 also equal to D, like this. So by using blocking assignment, we may have or get the wrong circuit for sequential design, sequential circuit design. Another example, before that, let's look at the non-blocking assignment. When we use non-blocking assignment, so each statement will be evaluated individually. If you write this using a non-blocking assignment, it is the same as you have to always block, where you have this one and this one. It's something like this. It's something like you have always post it, Q1 D, or you may use blocking assignment D, and then you have another one Q2 Q1. If you write using non-blocking assignment, so you will have something like this, where you have two always block. And if you have two always block, of course, the Verilog compiler will create one by one. This one first, and you will get this one. And then the second one here, you will get this one. And now you will get the correct design, which is the two cascaded flip-flops. Yeah? Another example is here. When you use blocking assignment in designing a sequential circuit, and you have the equation and the statement here, you have two statements where you see the G is here depend on F here, right? So you may end up with this circuit, right, where F here, and this is actually F. This line, this is F, because F is X1 and X2, X1 and X2. So this is F, and you have F, and this is F, and you always X3. This one is X3, and you have G. So if you use you use blocking assignment, you will get this circuit. But if you use non-blocking assignment, you'll have this because it is evaluated separately, right? So you have F, which is X and X1 and X2, and this one is one circuit where you have F here, and F now is OR with X3, and you have G. So it's different actually. It's different, yeah. This one you will have G and F almost at the same time, but this one you will have G one clock delay, all right, one cycle delay. So it is different. So rule of thumb or guideline, when you want to design a sequential circuit, please use non-blocking assignment, means that use this symbol. But if you want to code or create the combinational circuit, the circuit that we have learned in chapter 3, so we use the blocking assignment, which is the equal sign. This sign or this symbol is for sequential circuit, and this one is for combinational circuit. Then you will be safe. Yeah. Okay. So that is the difference between the two, which is actually very important. Now look at what we call the register. So register is actually built from flip-flops. So we know already just now before this that the flip-flops is used to store one bit of information. So the input here is 1 bit, the output here is 1 bit. Okay. But when we have a set of flip-flops together, so we can use to store many bits or n bits of information, such as n bit number, right? The number is, for example, 4-bit number, 8-bit number, 16-bit number. So we can use, for example, if 8-bit number, we can use 8 flip-flops to store that 8-bit value. So the n number of flip-flop is actually referred to what we call as a register. Yeah. So the register is very important in digital design, where we use to store information, where we use to store data. All right. So it depends on how big is your register. So if your register is 4-bit, so it is used to store 4-bit data. If your register is 8-bit, it is used to store 8-bit register data. And again, a common clock is used for each flip-flops. So it's this. Yeah. For example, this is we have 4 flip-flops here, and it is used to store 4-bit information. The input is A and the output is Q here, and this is of course need to connect to the same clock signal like this. This is what we call a 4-bit register. And to create a 4-bit register in Verilog is straightforward, easy. We know how to create one flip-flop already. So to create a register is to increase the size of the input and the output based on the what size of the register that we want. So for example, in this case is to create a 4-bit register. So we have A in this case to be 4-bit, which is 3 to 0. And the output, of course, is now 4-bit, Q3 to Q0, A3 to A0. And look at this. The way we code or create the flip-flop is actually the same as the way we create the flip-flops. The only difference is the size of A and Q. And again, we have the register now, a 4-bit register. If you have 8-bit register, so change this to 7, here to 7, and you will have the 8-bit register. And this is the simplified circuit or FBD, functional block diagram of the 4-bit register. Right? We have 4-bit input and 4-bit output. And of course, we have the positive edge clock here. And we have this. And now, in this case, this circuit, the data, if it is available in A3, not A3, all the A, if the data is available here, and when the clock is active, means that the positive clock edge, so the data will be latched into the flip-flop, right? Will be in the flip-flops or register. In practice, actually, we can control whether we want to load the data into the flip-flop or not. So in this case, we use what we call the parallel load register with reset, or if in this case we have the reset signal. So for example, we want to create flip-flops that will load the data only if we allow the flip-flop to read the data, to get the data in. So what we do is actually this. So we can have a multiplexer here. This is T, this is Q. And this is data in. For example, data in. And let's say this is 4-bit. And of course, this is 4-bit. This is 4-bit. And here we have load. We call it load signal, right? So when load equal to 1, so the data will go to the register. But if load equal to 0, the data will remain the same. So we need to have this feedback. Right? So now we can control whether we want to get the data or to put the data in the register or not, using this load control signal. When load equal to 1, then we read the data into the register. But if load equal to 0, although the clock is active, now the data will be always remain the same, because we have this. So now how to create this in Verilog? Easy. We can use the, again, always block. And we have the clock here. You need to write post h clock. And let's say the name is CLK. So now we have, if load equal to 1, then Q should be equal to this is Q equal to data. But if load equal to 0, Q should be remain Q. So no need to write anything, because the Verilog code and the Verilog compiler will know this already. If load equal to 0, so Q output here will remain Q. So this is how we create the load. Now let's see if we have another signal. We call it a reset signal. Means that we can reset this register to 0 anytime when we want. So we add another signal. We call it reset. and this is active high in this case. So to write the code for this, again, we use the behavioral code. So always post age clock. Now we need to include the reset into the sensitivity list because this is important. All right. And if our reset is positive or active high in this case, so we need to have post post age reset. This indicate that it is positive or active high reset. And now we can write the code to describe this. And because the reset is a high priority signal, so we need to check for reset first. So if reset equal to 1, or if reset, so Q should be equal to 0. Right? The output of our register should be equal to 0. Q should be equal to 0. But if reset equal to 1, Q should be equal to 0. But if reset equal to 0 or not active, so this should be else, right? Else. Now the output Q will depend on another signal, which is called the load signal. So else, if load equal to 1, then Q should be equal to data done. All right, no need to have the else statement here because the Verilog compiler know already. If load equal to 0, then Q should remain Q. So this is how. And again, when we write post age in Verilog, and it is for reset, it is actually not sensitive to the age. Yeah, not sensitive to the age. It is actually level sensitive. Means that whenever the reset signal is positive, all right, whether you are at the edge or this point or this point or this point or this point, it is always reset this register to 0. But this is a requirement in Verilog, all right, and it is called an asynchronous reset. Asynchronous reset. So back to this. So this is when we draw the functional block diagram of the 4-bit. For this one, we draw in the compact view where we have this is 4-bit, but when we expand this to every flip-flops, so we can have the circuit like this. This is actually the same circuit, right? So yes, of course, you need to build the 4-bit register using the hierarchical design technique. So you can try to do this. So you can create your register using hierarchical design technique also. This is not hierarchical design. This one is not hierarchical design because we define uh, the structure, all the structure of the register here already using this code only. Hierarchical means that you create one part of the register here and you connect with the other one using the module instantiation. Remember? So this is the same as what we have here. Yeah, same thing. And the code is the same. See, we have the clock reset load AQ, post H clock, and post H reset. And if reset, Q equal to 0. If load, else if load, Q equal to A or in the input. And this is called asynchronous clear or asynchronous reset. And this is how we create a bigger circuit or bigger and flexible code for creating the register. So for example, our register is 16-bit in size, and we use the parameter here n equal to 16, means that n hold the value of 16. And here we have the input, okay, 1 bit clock reset load, and we have input n minus 1, which is 15 to 0, right? Because n is 16 minus 1 is 15 to 0 A, and the output is 15 to 0 Q, and we have this. And whenever we want to change these to 8-bit, we in this code we just change this to 8, and everything here changed to 8, and minus 1, 8 minus 1, 7 to 0, which where we have 8-bit, and this also. And if you want a bigger register, so you can have this n equal to 32-bit, for example, and everything here will be a 32-bit. So this is very useful technique in designing a digital system, where sometimes we want to upgrade our design from a smaller design, 4-bit design to 8-bit design, or 8-bit to 16-bit, or even bigger. So we by using the parameter like this, we can change the size anytime as we want, right? Now we have this, but before we continue this, let's have a short break, 5 minutes before we continue.